Hi, welcome to module 37. In this module, we are going to look at the controller for the GCD machine that we were talking about. So, as I mentioned, the notion of a controller is a circuit. So, this is not some magical thing. It is also going to be a circuit, and I already hinted that it is going to be a state machine. So, it is going to be a circuit that will tell the data path elements on what is the sequencing of the data. So, we have inputs that are going to be at the subtractor and whatnot. So, the subtractor will keep subtracting all the time. Similarly, the comparator will be comparing all the time, but the registers, once you lose data, you cannot do anything about them. So, we need to control what values are getting into the registers, and the data path elements had various things. So, let us look at the controller's picture here. The data path elements are supposed to take select lines at appropriate times, and accordingly the registers will get values. And similarly, it is supposed to produce 3 output lines. The data path element will produce a greater than b, a equal to b, and a less than b as 3 output lines at appropriate times. The data path element also takes output enable as an input. All these signals are supposed to come from the controller. Whatever you see here are all going to come from the controller. So, 1, 2, 3, 4 lines here and this output line here are all going to come from the controller. These 3 lines are actually input to the controller. Clock and reset are something that is common, right. So, the controller also takes clock and reset. Besides these, there is also a line called go that the controller will take, and it will generate a signal called done, which will come from the controller. So, we need all these different things for the controller to do. So, let us see how to go about doing this. So, we are at module 37 and I am going to show you how to do this. So, in the last class also I talked about the notion of, in the last week's lectures I talked about the notion of state machines, right. So, we want to now think in terms of a state machine. What is a state machine which can actually drive various signals supposed to do? So, remember the canonical model of the state machine. There is something called the input forming logic, something called the state register, and something called the output forming logic. But we do not draw the circuit directly, right. We always did a state machine, and from the state machine we synthesize the circuit. So, what I am going to do is I am going to draw the state machine which can help us achieve this. So, let us think about what are the different kind of states that we will need. I am going to start with something called the initial state. So, I am going to call the state S0. So, the S0 is supposed to be an initial state, and when I reset the machine or when I do a start, the state machine is supposed to come to the reset state. So, I have that, and remember the protocol that we had is the external world will place the 2 inputs at input in1 and in2, and then will turn on a signal called go. So, if go is 1, then I can start processing, which means the state machine is supposed to tell the data path to take inputs and so on. But if go is not 1, which means the external world is not ready with the inputs, then the controller is supposed to wait for the go to become 1. So, the first thing I am going to draw is I am going to say that if we do not get go, so this exclamation means not off. So, if go is not 1, remain in this state itself. However, if we get go, we can start processing the external inputs, right. So, what is it supposed to do now? This controller, if go is on, I assume that the inputs are going to remain stable from the external world, and you got the go signal from the external world, which means the first thing that the data path must be doing is take the values from the in1 and in2, and it is supposed to put it in the registers A and B. To be able to do that, let us look at the data paths picture. Let us look at this picture here. So, let us assume that in1 and in2 are already ready. We are supposed to put the value of in1 in A and in2 in B. How is this possible? It is possible only if A select is 1, B select is 1, A load is 1 and B load is 1. So, we should have A select, B select, A load, B load all of them should be 1, so that in 1 gets copied into this register and in 2 gets copied into this register. So, this A select and B select sets up these multiplexers to select the appropriate input. So, if these are 1, input 1 will appear as input to the A register, input 2 will appear as input to the B register, but that is not enough. Unless you have A load equal to 1, the output of A will not copy the input of A register. So, we also need A load and B load to be 1, so that we can do the copy. So, what I am going to do is I am going to have this state called S1. So, remember, so I will just write down what these different states are supposed to be. S0 is the start state. So, this is the beginning. S1 is a state where I am supposed to load the values from the external world, load values from the external world. So, S1 is supposed to be that, and when S1 happens, what I am supposed to do is I am going to turn on several control signals. What are the different control signals? We know that the A select must be equal to 1, B select must be equal to 1, then we have A load equal to 1 and B load equal to 1. So, once I am in this state S1, I am supposed to turn on all these different values, and once these are there, now the data path will have the values A and B. So, let us again go to the data path, let us see what will happen in the next cycle, right. So, let us say the values A and B are in the registers here. So, in the registers A and B, let us assume that A and B got registered. What is the data path supposed to do now? A and B will be compared, you will get 3 different outputs here, and A and B will automatically appear as inputs to subtractor. After some delay, the subtractor will give some results and they will appear in A minus B and B minus A. So, what we are going to do is we are going to wait for one cycle, so that all the values get loaded. So, remember, once you place the control signals, let us say A load and B load equals to 1, only in the next clock cycle the values of A and B will be available in the register. So, A load and B load, both of them are inputs that are going to be sampled by our register, and when both of them are 1, the corresponding inputs will be copied, but the output of the register will be available only in the next cycle. So, in this one cycle, what I am going to do is I am going to wait for the inputs to come. So, S2 is supposed to be a wait state, and in this wait state I am going to wait for inputs to load. I am going to wait for the inputs to load. So, once the inputs are loaded, then the data path will have all the correct elements, the comparator will have the correct output. So, at this point the first thing I have to do is I have to go and look at comparison. So, S3 is supposed to be a comparison state. At this point the controller is supposed, so this is a comparison state. In this comparison state, what we are going to do is we gave one cycle for the comparator would have taken A and B and would have compared it, and the outputs less than, greater than or equal to would have come to the comparator stage. So, this is the compare stage, and there are now 3 possibilities from the compare stage. The 3 possibilities are that A is actually greater than B, A is equal to B, or A is less than B. So, A is greater than B, A is less than B, and A is equal to B. So, these are not the inputs directly. So, this is actually given by the condition that we have a input line called A greater than B. For A less than B, we have a wire called A less than B, and for equal to B, we have a line called A equal to B. So, the meanings of that is in the bracket. So, for each one of them I am supposed to do a different thing, right. So, when A is greater than B, what I am going to do is I am going to go to a state called S4, and what is this state supposed to do? Let us go back and look at the algorithm. If A is greater than B, A equals to A minus B, right. Now, let us look at the data path. So, the data path I have A minus B here, right. So, I want to take A minus B and put it into A. If I want to do that, then A select must be 0 and this load should become 1. So, these two conditions must be there. I should make A select equal to 0 and A load should be 1, so that the result A minus B gets registered into this one. So, that is what I am going to do now. In state S4, what I am going to do is, so state S4, I am going to make A select equal to 0 and A load equal to 1, so that the A equals A minus B gets done. I will have another state called S5. In S5 I have to do the reverse. In S5 I have to do B select equals to 0 and B load must become 1. The reason why that should happen is we want B equals B minus A. So, this is for A equals A minus B. So, this is for accomplishing A equals A minus B, and S5 is for accomplishing B equals B minus A. And once these things happen, and the other thing that can happen is that we can have this another state where everything seems to be done. So, whether it is greater, whether A is greater than B or B is greater than A, either way what I am going to do is, since the results are coming from the subtractor, so I am going to go to a new state, and in this state I am going to again wait so that all the values get to the proper registers. So, A should get A minus B or B should get B minus A, and for that, once I turn on the load equal to 1, only in the next cycle it will be available as output, but once it is available as output from the corresponding registers A or B, I am going to be ready to go and compare them once more. So, that is what this state machine is supposed to do. So, at S4 and S5 we know the results of the comparison. At S6 we let the register take the corresponding values, so that in the next cycle they go into the register. In S6 they go to the register, and at S3 it is the comparison state, right, we are ready to compare once more. So, this gives us the while loop. The while loop is while A is not equal to B, right. So, this part is taking care of while A is not equal to B, but if A is equal to B, that is the exit condition. I am going to call this the state S7, and in this state S7, so S7, so again let me write this down, S6 is a wait state and S7 is called the done state. So, we are done with all the work. So, S7 is called the done state. When S7 equals 1, when we get to state S7, what it means is the register A has the correct value, actually A and B both have the correct value. What I want is, if I go back to the data path, I said we will have to take the value of A and copy it to the output register, so that this output register will keep the previous output. Even if there is a new computation that is going on, this output will be held as long as it is necessary. So, let us say output is enable, so we turn on output enable, we copy A from, we copy the value of register A into this output register. This will remain at the output even when the input changes. This will change only when the next result is available. So, till then this output register will keep the value. So, this gives enormous time for the external world to copy output. So, what we are going to do is, in S7 we are going to say that output enable, right, at this point from S7 we will turn on output enable, we will make output enable equal to 1, so that output gets copied. We will also give this done signal equals 1, because this is a state which tells us that the while loop has ended. In some sense this is equivalent to printing A, right. So, this is the end of the loop. Then once this is done, I am ready to go and take new inputs, and at which state I am ready to take new inputs, I am ready to take it from S0. So, I am going to connect this back to S0, so that once done signal is ready, it means I have processed the current inputs, I am now ready to take the new set of inputs. And what is the protocol for that? So once done becomes on, till done becomes on, the external circuitry or external world cannot give new inputs, right, because we are going to be processing here, we are going to be one of these states, suddenly we cannot say go back and look at new inputs and start processing. So if we are in one of these states, we will have to wait till this whole transition gets over, we should come back to S3, and then from S3 we come to S7 at some point of time, that is the end of while loop. Once S7 is done, then you come to S0. At this point the external world can give new inputs, it can choose not to give any new inputs at all, but if there are new inputs, the external world will keep the new inputs ready, and once the new inputs are ready, then it will give a go signal, and only then the state machine will continue. Otherwise, if the external world does not give a go signal, it will stay in the state S0 itself, but when it is in S0, the output will be the previous computation that you have done. It will keep placing the previous output coming from the whole state machine, that will stay on the output till this go signal comes. Once the go signal comes, the output will still remain as the previous output till this whole thing processes and generates the new output. So this is the state machine that we want. So you can see what are all the different things that it is taking. So reset is an input, go is an input, then A select, B select, A load and B load are actually outputs, A greater than B, A less than B and A equal to B are actually inputs to the state machine, output enable and done are outputs of the state machine. So I have not drawn this as input slash output, and in fact in many places I have not even drawn what combination is supposed to take you from one place to the other. In many places they are only implicit. What we are going to assume is that by default all the outputs are 0, so A select, B select, A load, B load, output enable, done, we will assume that by default all of them are 0, only when they become 1 I have indicated them. And these are the three places where we need inputs also. So A greater than B, A less than B, A equal to B, we need some input to the controller, and go is another place where we need some input to the controller. The other states are not even processing the inputs to the controller. S7, S6, S5, S4, S2, S1, all of them do not process inputs to the controller, only S0 and S3 are processing inputs to the controller. S0 is a place where you are getting something from the external world, S3 is the state where you are actually comparing where you are getting the result of the comparator. So this is my overall controller, and what we essentially have is, we have in some sense the circuit, we have to now go and design a circuit to do this. So we have the state machine, we have to design a circuit to do this. What we will do is, in a subsequent video, instead of designing a circuit using gates and flip flops and so on, I am going to go ahead and straight away draw the state diagram for this using Verilog. I am going to design this whole thing in Verilog directly. So in the next set of videos, in the next sequence of videos, what we are going to do is, I am going to design the data path, and I am going to design the control path, and I am going to write a top level module which takes the data path and control path together and stitches it up together. So we will start with that, and then we will slowly build all the different components that is supposed to go in together, and we will be writing Verilog directly for those things. So this brings me to the end of module 37. In modules 38 onwards, you are going to see how to write Verilog for various things, and in the process we will also learn some basic fundamentals of Verilog. Some of the things that I have not talked about so far, we will start seeing them in Verilog. So from 38 onwards, you should keep this picture that I showed in mind, and I will also put them up as PDF so that you can see it online. So keep that picture in mind. When we write the Verilog description, you need to have that picture in mind so that the whole thing falls in place. So I am going to show how to do that from module 38 onwards. So this brings me to the end of module 37. Thank you, and I will see you in a little while. Bye bye.